Good morning, dear students. Welcome to another session of microwave and antenna. So, in previous session, we started off our discussion with the strip lines, and in that we discussed regarding the schematic of this strip line, how the field lines exist, and why it is called as quasi TEM. So, these all things we had discussed, and we discussed regarding what micro strip lines and what is the characteristic impedance and few other parameters, and we solved even problems, and then we discussed regarding what are the losses which are present in the strip lines, that is ohmic losses, then the dielectric losses and the radiation losses. So these were a few of the things what we had discussed in the previous sessions. So moving further with the next aspect. So also we discussed regarding the quality factor of the microstrip lines, which is again dependent on the alpha C and alpha D parameters. That is the attenuation constant due to conducting element and attenuation constant due to the dielectric element. So these things we have discussed. So next one which we have is the parallel strip lines. So these parallel strip lines, as it is represented in this diagram, we can see that there are two conducting elements. Uh, present in between these two conducting elements. I'll be having the dielectric material. I'll be having the dielectric material. So this will act as a parallel transmission line. It will act as a parallel transmission line. That is two lines which are running parallel to each other. Now, what is the advantage of such this thing is, in previous we could see that we had only one conductor placed on the substrate. Now we have two conductors which are placed on either side of the dielectric substrate. So because of which I can have connections at this point and connections at this point. Now, as we observe here, what we have is we have the dielectric material which is having the dielectric constant and the permeability which is given by epsilon d and mu d, and the distance between the two conductors is d. And here we can observe that this dielectric material is assumed to be placed along the z axis. It is placed along the z axis, due to which I'll be having the electric field associated along the y axis and the magnetic field associated along the z axis. So here, this is how this parallel strip lines are observed. Then apart from this, we also look forward for another parameter which we call as epsilon RD, which is nothing but a relative dielectric constant. So if you remember, epsilon is basically given by what? Epsilon naught into epsilon R. So this epsilon RD is nothing but this parameter. This parameter. And when you're specifying the permeability, you are considering, a permittivity, you are considering both these together, the multiplication of these two together. So here D, say a subscript, what they are specifying right here or here, it is just to identify that this is because of the dielectric material. This is associated with the dielectric material. So otherwise this is mu, this is epsilon, and this is epsilon R. So this epsilon is again equal to what? Epsilon naught into epsilon R. So when I consider the dielectric constant, it will be consisting of the subscript just to differentiate. That is, the subscript is D to identify that it is due to the dielectric material. So this is a parallel strip line. Now, along with this, since as I just specified that this is nothing but two lines which are placed in parallel to each other. So in the previous session, we had discussed, right, that along the transmission line, we have the impedance parameter, we have the conductance parameter, and along the parallel part, we have the conductance parameter, and we have the capacitance parameter. If you remember this, so this we had discussed. So these are the distributed elements. That is, we have RLGC parameters which are distributed over the transmission line. And since we are dealing in wave range, right, in which the frequency is very high. If the frequency is very high, then as we had seen that the length associated, if frequency is high, what happens to lambda? Lambda is reduced. Lambda will be less. So in that case, what happens is the length becomes very much greater than lambda. So that is what we had observed in the previous sessions. That is, at the starting, we had gone through some derivations associated with that. So because of that, what we have is we have to associate the distributed parameters along this strip line. That is, this is acting as a transmission line along which the distributed parameters are associated. So based on that and the derivations what we had done, we have the same representations over here, that is RLGC parameters, but they are given in terms of what previously I did not have the dielectric or the permeability associated with these things. But now since we have to associate them, what happens is directly I cannot refer to those, but I can just see what are the values of RLGC parameters and then use it in identifying the Z dot and identifying, say, the attenuation parameter or the propagation constant. So these are the factors what we can look out in parallel strip lines. So now let us come to what will be the distributed parameters, that is RLGC parameters in the parallel strip line. So again, the quasi-TM mode comes into play as we had seen in the starting strip line discussion. Then in this case, again, as I specified, electric field is along y direction and magnetic field is associated in the x direction. That is what I specified. That is the conductor is placed along z direction and electric field will be moving from one point to the other point because of the current flowing through this. Therefore, it will be associated in the y direction. And say if current direction is this side and I am having the electric field associated in this direction, then magnetic field has to be 90 degrees with respect to electric field and it cannot be along this direction. So it has to be along the other one, that is the x direction. So that is that part is given over here, wherein you are considering that the wave is propagating along the z direction. If wave is propagating along the z direction, I have the electric field along the y direction and the magnetic field along the x direction. We are assuming that the width w is much greater than the distance. That is, the w parameter is much greater than the distance between these two conductors or the height of the dielectric. So that is what we are considering over here. Then we have something called as fringe capacitance, in which we'll be looking forward in the next part. That is in coplanar or shielded coplanar strip lines. We'll be observing what is the fringe capacitance. So we are neglecting those. Then apart from that, so these parameters are associated. Then along with that, we have mu and epsilon. Now we can have permeability, that is mu because of the conductor or because of the dielectric constant, and epsilon because of the dielectric, because of the conductor and because of the generally for the dielectric constant. So these are the previous assumptions what we had seen. So based on that, we can have the inductance parameter, and since it is a distributed parameter, right, all these are distributed parameters, therefore their unit, if you just observe, they are given as per meter. They are given as per meter. So here you can see it is Henry per meter, this is Farad per meter, this is Ohm per meter, and this is the mho per meter. So in this case, the impedance, that is a distributed parameter impedance for the parallel strip line, is given as mu c into d divided by w. Similarly, when we consider the capacitance, it is epsilon d. So this is what, this is the permittivity, which is actually including both. It is epsilon naught and epsilon r. So in order to distinguish that this is due to a dielectric, we just replace it as epsilon rd, just the representation. So this is combination of both absolute permittivity and relative permittivity. It is product of both. So it is epsilon d into W by d. So here, as in this case, if we can observe that mu c is the permeability due to the conductor, which is due to the conductor, and this one is the permittivity, which is due to the dielectric material or the dielectric slab. Now, next, the resistance is given by the surface resistance. That is, you had seen in the previous discussion wherein we saw what is Rs equal to. Rs was given by this parameter. That is, here we had observed it. So this one, surface resistance. So which is we sometimes term it as surface resistance or surface skin resistance, which is given by square root of pi f into mu by sigma. Or if it is associated with the skin depth, it will be given by 1 by delta into sigma, where delta is given by this parameter, that is square root of 1 by pi f mu into sigma, and this one will be in terms of centimeter. So if we consider that there is a skin resistance associated with the parallel strip lines, that is for the conductors, then its resistance can be given by this equation, which is 2 times Rs divided by W. And when you make the substitution for Rs, you have 2 by W into square root of pi into mu c divided by epsilon sigma c. So again, mu c and sigma c are due to the conducting elements or due to the conductors. And here Rs is termed as the skin resistance or the surface skin resistance. And we have sigma c, which is the conductivity of the conductor. And the last parameter what we have is the g parameter, that is g is equal to sigma d W divided by d. Again, this parameter comes because of the dielectric material what we are considering. So in this case, we have sigma d, which is the conductivity associated with the dielectric substrate. So these are the distributed parameters, that is RLGC parameters, which is resistance, capacitance, inductance, and the conductance parameters of the parallel strip line. So when we have RLGC parameters, I can identify what is the characteristic impedance. So if you remember characteristic impedance from the the very first discussions what we had, wherein the Z0 is given by what? It is given by Z by Y. And in between we had applied the binomial expansion. We had applied the binomial expansion to this, and we had obtained Z0 nearly equal to L by C. So that equation directly we are utilizing over here. So that Z0 is nearly equal to square root of L by C. So initially it is actually Z by Y. And when you apply the binomial expansion and simplify that entire parameter, we obtain is Z0 nearly equal to square root of L by C. So when I substitute L and C from the above equations and simplify it, I'll be getting the characteristic impedance, which is given by this equation, which is 377 divided by square root of epsilon RD d by W. Again, observe this. This is the relative permittivity of the dielectric constant. It is not the epsilon what they are specifying, wherein epsilon is epsilon naught into epsilon r. Just to segregate that it is due to the dielectric, we just add the subscript epsilon d is equal to epsilon naught into epsilon rd. So in this case, this is the value what you are using over here. So it is 377 divided by square root of epsilon rd into d by w. And the condition what you had considered was w is much greater than the d value. That is, width of the conductor is greater than the distance between the conductors. That is, in the parallel strip line, width of this conductor is greater than the distance between these two conductors. So this is a characteristic impedance value what you get after substituting L and C in this equation. And if I want the phase velocity for the parallel strip line, I can make use of this equation, that is Vp is given by omega by beta, or it is also equal to 1 by square root of LC. And when you make the substitution, you will be able to simplify the equation as given here, that is C divided by square root of epsilon RD. Again, this is relative dielectric constant, relative dielectric permittivity. And what we are doing is we are assuming that mu c is equal to mu naught, which is 4 pi into 10 raised to minus 7. So we are assuming that condition, and we are simplifying it to this equation. Now next, attenuation. In order to obtain the attenuation, we can obtain it from the propagation constant, which is actually given by alpha plus j beta, in which this gives you the attenuation parameter, this gives you the phase constant. This is the attenuation constant and this is the phase constant. Overall together it is the propagation constant. So if we remember, we had obtained an equation for the propagation constant, which was given by square root of z into y. And what is z? Z is equal to r plus j omega l, and y is g plus j omega c. And again, if I apply binomial expansion to this equation and simplify it, I'll be getting gamma, which is equal to 1 by 2 into r into square root of c by l plus g into square root of l by c plus j omega square root of lc. So here we can see that this equation is alpha, and it is given by plus j beta. So in this case, this entire equation is relevant to the attenuation constant. So here we have the attenuation constant, which is equal to this part, that is real part of the propagation constant. And omega into square root of LC gives you the phase constant, gives you the phase constant. Now here, if we just observe again, this alpha is made up of two parameters. That is, one is r into square root of c by l, and another one is g into square root of l by c. So these are the two parameters which we have. Now, since this is a resistive parameter associated with this one, this actually leads to attenuation due to the conducting element, and this one is attenuation due to the dielectric element or the dielectric substrate. So therefore, we have alpha c, which is given by half into r square root of c by l, half into r square root of c by l. And when you substitute r, c, and l from the above equations, you will be able to simplify it as this equation, that is 1 by d square root of pi into f into epsilon d. Again, this is equal to epsilon naught into epsilon rd, this divided by sigma c. And alpha d is given by the next parameter, that is half. You take this half inside, that it is half into g square root of l by c. Again, substitute lcg values, and you will be getting 188 sigma d divided by square root of epsilon rd. So these are the equations what we get for parallel strip lines. So next, we'll just look into a problem associated with the parallel strip line. So in this case, we have a lossless parallel strip line has a conducting strip width of W. The substrate dielectric separating the two conducting strips has a relative dielectric constant. So relative dielectric constant implies that it is epsilon Rd, which is equal to 6. And this is actually the beryllia or the beryllium oxide, and a thickness of 4 millimeter. So this thickness is nothing but the dielectric material's thickness, which is given as D. Now we need to identify what is the width value for of the strip line, so that I can have a characteristic impedance, that is Z naught, which is equal to 50 ohm. Then what is the strip line capacitance, what is the strip line inductance, and what is the phase velocity of the wave uh, in the parallel strip line. So in order to estimate all these parameters, we'll be making use of the equations what we have discussed, and we need to substitute those values. So in this case, we can just observe over here. So first one, we need to identify what is the width. So width, as we had seen, it is given by 377 divided by square root of epsilon RD D divided by Z naught. Now here we want Z naught equal to 50 ohms. Therefore, Z naught will be 50 ohms. Epsilon RD, it is 6. And D value is given as 4 millimeter. So if you substitute these values, right, you will be getting the width, which is around 12.31 millimeter. 12.31 millimeter. So that will be the width of the strip line, for which I'll be getting a 50 ohm characteristic impedance for the given parameters over here, that is the D and the epsilon RD parameters. So next I have to identify the stripline capacitance. So C is given by the equation, that is the starting equation what we had discussed, that is here we can observe we use epsilon D into W by D, and if for inductance we make use of mu C D divided by W. So in order to estimate the capacitance, we make use of epsilon D W by D. Now in this case, epsilon, again as I specified, epsilon we write it as what? Epsilon naught into epsilon R. And just to segregate it as a dielectric material, we just put the substrate. So epsilon D is actually equal to epsilon naught into epsilon R, where epsilon naught is 8.854 into 10 raised to minus 12, and epsilon RD is 6. So this is the product of both. So this is epsilon RD. This is this is epsilon D. Next, you have the width of the strip lines, which is 12.31 into 10 raised to minus 3. There is a typo error over here. It is not 101 raised to minus 3. It is 10 raised to minus 3. So just rectify that. It's just a typo error over there. So it is 12.31 into 10 raised to minus 3 divided by 4 millimeter. That is 4 into 10 raised to minus 3. So when you calculate the capacitance, it turns around 163.50 picofarad per meter. Next, the stripline inductance, when we have to estimate, we make use of the other equation, that is L is equal to mu C into D divided by W. Now here, since mu D parameter, the relative permeability is not given, what we do is we consider mu C equal to the mu naught value, where mu naught is 4 pi into 10 raised to minus 7. So we are assuming that condition, and we are substituting it in this equation, that is mu C is equal to mu naught, which is 4 pi into 10 raised to minus 7 into 4 millimeter divided by 12.31 millimeter. So when we substitute that and simplify it, I'll be getting the inductance, which is around 0.41 microhenry per meter. And lastly, about the phase velocity, as we had seen over here, the phase velocity is given by these parameters. If you have estimated L and C, you can use directly this equation, that is 1 by square root of LC, or else you can refer to this equation. So you substitute either one L and C in this equation, or use C divided by square root of epsilon RD. So when you substitute, make use of the either equation, you will be getting a phase velocity of 1.22 into 10 raised to 8 meters per second. So this is in association with the parallel strip line. Now, next topic which we have is coplanar strip line. Now, it is different from the parallel strip line. So in what way, we can just observe over here. In previous case, what was the thing? You had a you had a strip line over here and you had a strip line over here. So which was a parallel strip line. Now in this case, what happens is you have two strip lines which are placed above the substrate, Whereas in parallel strip line, if you just observe what you have a dielectric material in between. And on one end you have one conductor, and on the other end you have the other conductor. This is the parallel strip line. Coplanar. Now these two are present in the same plane. So here you have a dielectric material, and on one end of the dielectric material, you will be having two strip lines which are placed parallel to each other. And along with that, what is done is one of the strip line is grounded. Now, what is the advantage of such kind of structure? Now, as we had discussed previously, in microwave also, when we are developing the integrated circuits, we need to make connections. And when the connections happen to be associated in parallel terms, right, then in that cases, we can look out for these coplanar strip lines. We can look out for connection associated with the coplanar strip lines on the same end. So that is one of the advantages what we can take from these. Then apart from these, what happens is, if you just observe uh, in the previous case, on both sides you are placing the conductors, but in this case on one side you are placing both the conductors. That is in the parallel. As compared to the parallel, schematic wise you can just make out the differences. And now here a few parameters you can just check out. That is, d is the height, or the height of this dielectric material which is present, and w is the width of the strip line, and s is the separation between these two strip lines. And mu and epsilon, that is mu d and epsilon d, are the permeability and permittivity of the dielectric substrate. Now, when we are considering these kind of structures, we can see what is the characteristic impedance. The characteristic impedance is given by 2 times P average divided by I naught square. So generally, when you have power, right, in very simple terms, when we write it as, say, as I square, say Z. We write it in this one. When we want the average, right, say if I want the average, I'll be taking it as 1 by 2, that is half of this P value. So therefore what happens is, this Z will be equal to 2 times P average divided by I square. So that is what is utilized over here. So here the characteristic impedance is 2 times P average divided by I naught square, where what is I naught? I naught is the total peak current in one of the strips. And here P average is the average power which is flowing through the positive Z direction, because we are assuming that this strip line is placed along the positive Z direction. And because of this, again, I have the electric field associated in the Y direction and magnetic field associated in the Z direction. So therefore, we have characteristic impedance of the coplanar strip line, which is given by Z naught is equal to 2 times P average divided by I naught square. Then we have from your pointing theorem, okay, based on the electric and magnetic field also, we can there is a pointing vector what we specify. We can have P average, which is given by equal to 1 by 2 real part of this integration. So here it is double integration of cross product of E and H conjugate, and this is nothing but a unit vector along the Z direction. So why like that it is the planar, the thing is placed along this direction, and the wave will be propagating say along the Z direction. And when the wave is propagating along the Z direction, you have a electric field associated in the Y direction, and you have a magnetic field associated in the Z direction. And when you take the cross product, its unit vector will be along the Z direction. So that is what it is resembling over here. So now here we have P average is equal to half into real part of this integration, in which it is the integration of cross product of E and H conjugate and a unit vector along the z direction, and the difference integration is associated with respect to x and y. Now here Ex, that is field, will be associated only in the x direction, and H will be associated in the y direction. Therefore, directly we are specifying over here as Ex is the electric field intensity in the positive z direction, and Hy is the magnetic field intensity in the positive y direction. And star indicates that it is a complex conjugate. It's a complex conjugate of H. So based on this, we can look out for another problem over here. In this, a coplanar stripline carries an average power of 250 milliwatt and a peak current of 100 milliamperes. Determine the characteristic impedance of the coplanar stripline. So here I naught is given. I naught is 100 milliamps and P average is 250 milliwatt. So here we can use this equation directly, that is 2 times P average divided by I naught square, to identify what is the characteristic impedance. So when we make the substitution and simplify it, we'll be getting Z naught near equal to 50 ohm. So this is the characteristic impedance of the coplanar strip line. Now the last topic in this part is shielded strip line. So what is the difference between this and the rest? So in previous you were observing that, so here we can observe that these strip lines are present above the substrate. In parallel, we can observe that these are present above the substrate and below the substrate. So similarly, previous microstrip lines also we observed that strip lines are present above the substrate. Now, in shielded strip lines, what happens is the strip line has to be guarded. That is, it has to be shielded. How that shielding is looked forward? It is done with the use of the dielectric material. Now, in this case, what is done is it will be actually partially shielded. So, in this case, what happens is you have a strip line, and surrounding the strip line, you will be having the substrate. So indirectly, what is done is the substrate, the strip line will be embedded within this dielectric material, within the dielectric material, and at the end of the substrate, we'll be having the ground planes. So here we have a ground plane. This is a ground plane, and this is a ground plane, and this is the substrate which is present or which is embedded within this dielectric substrate material. Now, based on the reference, okay, the Z naught equation for such kind of strip lines is given by Z naught, which is equal to 94.15 divided by square root of epsilon r into W by D into K plus CF divided by 8.854 epsilon r, its inverse. Now here K is just a factor which is associated with the thickness and the distance between the planes, distance between these two planes. So that K value is given as, 1 divided by 1 minus T by D, where T is the thickness of the strip line, D is the separation between the two ground planes. That is, these are the two ground planes. The separation between these two is given by D. Next, we have the fringe capacitance, which is given by CF. This is the fringe capacitance. So it is given by this equation, which is 8.854 into epsilon r divided by pi into 2 times k natural log of k plus 1 minus k minus 1 into natural log of k square minus 1. And the value to this one will be in terms of, that is the unit of this one will be in terms of picofarad per meter. It will be picofarad per meter. So now we actually in the next this thing again we'll look out to identify what is the Z0 parameters when these parameters are specified. So here we have a problem associated with that equation. A shielded strip line has following parameters, in which the dielectric constant of the insulator, that is the dielectric material, is epsilon r, which is 2.56. Strip width is 25 mils, strip thickness is 14 mils, and shield depth is 70 mils. So all parameters are specified. Find what is the K factor, find the fringe capacitance, and find the characteristic impedance. So K is given by what? K is given by 1 divided by 1 minus T by D. So thickness is 14 mils and D is 17 mils. The units are same, so no need to worry. So 1 divided by 1 minus 1 by 1 divided by 1 minus T by D. So when you substitute that value over here, you'll be getting K equal to 1.25. Now fringe capacitance. What is the equation for fringe capacitance? It is 8.854 epsilon r divided by pi into 2k natural log of k plus 1 minus k minus 1 into natural log of k square minus 1. And the answer will be in terms of picofarad per meter. So when I use that equation and substitute the parameters over here, so it is 8.854 into epsilon r. Epsilon r is how much? 2.56 divided by pi. Pi, instead of putting the pi directly, you can substitute its value, that is 3.1416. This is nothing but pi, into 2 into k factor, that is 1.25 into natural log of k plus 1 minus k minus 1 natural log of k square minus 1. So when you substitute and simplify this equation, you will get 15.61, and the unit of this one will be 15.61 picofarad per meter. Now lastly, the characteristic impedance, that is Z0. In order to estimate Z0, this is the equation what we have to use. So it is 94.15 divided by square root of epsilon r W by D, the K factor, plus the fringe capacitance divided by 8.854 into epsilon r, its inverse. So here again we make the substitutions in this equation. Epsilon r is 2.56, W by D, that is W is 25 and D is 17 mils, and K is 1.25. Epsilon, fringe capacitance, we got it as 15.61, and 8.854 into epsilon r, that is 2.56, and we take the inverse of this part. So when we simplify this equation, we get Z0 again nearly around 50.29 ohms. So this is what we are getting in this case. So this is the discussion associated with the strip lines.